Welcome to The Explainer. I'm your host, and today we are stepping right into the ring for the ultimate boxing match. It's you versus the Cambridge Computer Science 9618 syllabus, and we are targeting one of the most notoriously tricky heavyweights out there, assembly language bit operations. Specifically, we're talking about logical shift left, or LSL, and logical shift right, LSR. Now listen, mastering this exam isn't just about throwing wild punches. You've got to float like a concept and sting like evidence. It's all about your answer combinations, the jab, the cross, the hook. Today, we're going to break down the exact tactical strategy and methodology you need to master these calculations and absolutely dominate your exam paper. Let's get ready to rumble.
So why do students consistently hit a wall and get knocked out by multi-step bit calculations? Senior examiners see the exact same dilemma every single year, and it usually comes down to two very specific types of students. Let me introduce you to Alex and Sam. Now, Alex is the kind of student who overloads every single answer with raw computer science facts. Alex will write a massive, sprawling paragraph explaining exactly what a binary number is, what a register is, and what a shift operation does in theory. But there's zero actual analysis applied to the specific scenario. It's just a haymaker of facts that completely misses the target. On the other hand, you have Sam. Sam rushes. Sam sees the letters LSL and immediately starts shifting bits without even reading the rest of the question. Sam completely misses the command word requirements, ignoring words like evaluate or analyze, and just spits out a final hex value. Both Alex and Sam are throwing away massive amounts of marks. You shift the bits, you track the carry, but if the logic tangles up or you ignore the command words, you lose. Let's transform these calculations from a source of absolute panic into guaranteed hard-hitting points.
Here is our game plan for the explainer today. Number 1, core principles. Number 2, technical methodology. Number 3, securing method marks. And number 4, critical examiner warnings. Let's jump in.
Section 1, core principles, the rules of the game.
All right, let's talk about the rules of the ring. The Cambridge Assessment Framework prioritizes something called logical structured reasoning. This means they value analytical depth and systematic analysis way more than superficial breadth. It is absolutely not enough to just memorize that an LSL operation mathematically multiplies an unsigned integer by 2. That's superficial. You must understand the underlying mechanics. You need to explain that you are taking an 8-bit or 16-bit register, shifting every single bit one position to the left, padding the least significant bit with a 0, and pushing that most significant bit straight into the carry flag. This is where the PEEL framework comes into play. P-E-E-L. Point, evidence, explanation, link. This is your combination punch. Make your point about the shift. Provide evidence by showing the specific binary string from the question. Explain the mechanic of the 0 padding and the carry flag. And link it back to what the question is actually asking. If you just throw facts like our friend Alex, you get 0 method marks. But if you use the PEEL framework, you demonstrate the conceptual depth that Cambridge examiners are actively hunting for.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, moving on to a massive insider secret directly from the Principal Examiner Report. They explicitly state, candidates referencing cross-topic connections achieve significantly higher marks. This is how you secure the top-tier grades. The theoretical architecture of LSL and LSR doesn't exist in a vacuum. It relies heavily on integrating with other syllabus areas. For instance, how do your bit shifts affect a 2's complement integer? If you perform an LSL on a negative number, does the sign bit change? If it does, you've just triggered an overflow error because the mathematical logic is broken down. Sam totally missed this in the exam because Sam rushed. But you're going to connect these dots. You're going to use precise definitions and link your bit operations back to data representation principles. That is how you land the knockout blow.
Section 2, technical methodology, executing combinations.
Now we're shifting from theory into the actual procedural steps you need on exam day. This is the transformation phase. I want you to imagine we're taking Sam and Alex's flawed answers, crossing them out with a red pen, and rewriting them into a perfect green checkmark response right now. We are going to use the Computer Science Success Blueprint. It's a 5-step combination. Step 1, deconstruct the question. What exactly is the command word asking? Is it asking you to state, describe, or evaluate? Step 2, extract the relevant data. Grab the exact binary values, the register details, and the specific operation requested. Step 3, select your analytical framework. Are we shifting left, shifting right? Are we tracking the carry flag? Step 4, execute with crystal clear notation. Write everything out. And step 5, present your final answer using correct Cambridge terminology. If I put 60 seconds on the clock right now for you to rewrite a messy answer, this 5-step blueprint is exactly the structure you'd lean on to guarantee you hit every single marking point. Drilling down further into that execution step,
Your algorithmic thinking needs to hit some very specific targets. Please, whatever you do, do not try to jump to the final hex value in your head. That is a guaranteed way to drop marks. Instead, deconstruct the operation step by step. Literally extract the binary representations. Write out the original 8-bit string on your paper. Physically draw arrows showing the shift direction. Explicitly write down the zero padding on the correct side, right side for LSL, left side for LSR. And crucially, explicitly write down the new value of the carry flag before you even attempt to convert your final answer back to hex or denary. Select the appropriate data structures mentally and conduct rigorous testing on your own bits. Look at your answer and ask yourself, does this make logical sense based on the operation? This step-by-step decomposition is what separates the A-grade candidates from everyone else.
Section 3. Securing method marks, the ultimate safety net.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's talk about survival tactics. Here is a high-impact examiner alert directly from the marking schemes. Always show you're working. Even if your final answer is wrong, method marks can save you. This is the ultimate safety net. Let's say you're under pressure, the clock is ticking, and your final binary string is off by a single bit because of a silly miscount. If you just wrote down the final answer, you get a 0. But if your working clearly shows that you knew to shift the bits left, and it clearly shows you padding the empty space with a 0, the examiner can award you method marks for demonstrating the correct analytical framework. Executing your analysis with visibly clear working is literally the only way to salvage your grade if a calculation goes sideways. Never skip it.
Okay, it is time for an interactive workshop. Let's run a 60-second mental data scan challenge. Imagine a question asks you to compare operations, say an arithmetic shift left versus a logical shift left. How do you attack it? Well, you cannot just list facts like Alex does. You have to identify both similarities and differences. This is where your command of language matters just as much as your math. You need to use comparative connectives, words like whereas, however, or similarly, and you must support both sides with hard evidence from the binary representations. For example, your point could be, both operations shift all bits one position to the left. That's a similarity. But then your difference is, however, an arithmetic shift preserves the sign bit, whereas a logical shift does not, potentially altering the positive or negative value of a 2's complement imager. See how we just found the flaw in a basic comparison and elevated it? You're showing exactly how the bits behave differently to secure those high-level comparative marks.
Let's move into a 30-second speed writing mindset. When you're crafting your perfect PO paragraph, top-scoring candidates hit those higher-order assessment objectives by demonstrating deep evaluative thinking. This means you need to consider multiple solutions and analyze the trade-offs. Why would a programmer choose an LSR instead of an arithmetic shift right? You need to acknowledge the limitations, like what happens when you run out of bits in an 8-bit register. And most importantly, you have to justify every single decision with evidence. Don't just say LSL multiplies by 2. Say, an LSL effectively multiplies an unsigned integer by 2, provided that a 1 is not shifted into the carry flag, which would indicate an overflow limitation. That level of critical analysis is exactly what examiners are desperate to see.
Section 4. Critical examiner warnings. Defensive maneuvers. We are in the final rounds of the match, so let's pivot to defensive maneuvers. According to principal examiner reports, here is exactly where students throw away easy marks. I'm going to rapid-fire the top 3 mistakes so you can mentally checklist them right now. Number 1, forgetting to check overflow and edge cases. If you logically shift left and a 1 falls off the end of your 8-bit register, what happens? The carry flag is set to 1. If you don't state that, you lose the mark. Number 2, forgetting boundary conditions entirely. And number 3, and this is a big one, giving answers that are not specific to the question's context. Listen closely. If the exam paper gives you a scenario about using bit manipulation to control the motors of a robotic arm, your analysis needs to reference that robotic arm. If bit 4 controls the elbow joint and you shift it, talk about the elbow joint. Do not just spit out a generic textbook definition of an LSL. Context is absolutely non-negotiable. To help you lock in your exam strategy for test day, here is a highly actionable memory hack, right from the source material. Create a mnemonic using the first letters of key terms to remember your operations and your edge case checks. You need a cheat sheet in your brain.
Whether it's to remember our 5-step procedural blueprint, deconstruct, extract, select, execute, present, or to remind yourself to always check the carry flag, overflow, context, and boundaries. Find a mnemonic phrase that is goofy, memorable, and sticks in your brain, so when the pressure is on, you can recall the complete computer science answering system on demand.
So, we arrive at the final provocative question. Will you secure every method mark in your next examination series? You now have the 3 rules that guarantee top marks: command word decoding, PEAL framework application, and showing your step-by-step working. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep floating, keep stinging, and I'll see you in the next explainer.